is normalizing URLs and stuff. That's really something that Force 10 doesn't want to give to me, and I'm also not really interested in, because I want to use it as a monitoring system, and anything that changes the packet is unwelcome in this system. So that's why I didn't draw it in. The Zowie interface is 64 bits wide, and here there is a converter that puts these 64 bits into 128 bits and halving the clock rate with that. And that is just being copied through to the backend FPGA. And from the backend FPGA you can get the signal to block the traffic. So let's see what we get then from this FPGA. We get a 128-bit word with the entire frame. This is the first word you get, completely with the preamble. Ethernet starts with the preamble of 10101010 or 5555, if you will. And at the end, there is a special bit pattern to say, hey, now the Ethernet frame starts, and it starts with the destination MAC address. But then you also have 16 bits over, so here is the first part of the source MAC address. And if you remember that we are particularly interested with this last example in the source address, you see this is where we're interested in. And then you get more. You get the rest of the frame, more and more and more, until the last piece of the payload, and then it starts over again. You get the next frame. And for IDS purposes, this is fine. Your IDS people are interested in the payload. They are interested in bit patterns that are there that assemble attacks. But we are mostly interested in this kind of headers and in the source MAC address. And the first problem I encountered with this IDS system is that they didn't really care about this. So all the counters in the system, they didn't work with this word to change it, so this piece of data could be used. And that restrains your timing as well, because here they could do all kinds of things. Well, while this was coming in and they didn't do anything with it, well, I'm particularly interested in that. But there was enough resource, enough timing to do that. So what happens in the backend FPGA? The backend FPGA is so-called single data multiple instruction system. There was this guy called Flynn that in the 70s made a taxonomy saying you can have one processor with one set of data that's doing its job. In the 70s and early 80s you had this, the home computers and the PC that were doing this. This PC got data in, was processing it, got data out. Then there came the superscale processors like your Pentiums and stuff that can have multiple data and multiple PC, dual core and that kind of things. You can also have a CPU that does one instruction on multiple data. Examples of that are graphical processors that get one instruction and different processors do different pieces of the screen. But this is a system that uses one piece of data and applies multiple instructions on that. And that's not really, really common. But for this purpose, it's really suitable, and especially for the IDS purposes, it's really suitable because you have a huge amount of patterns you want to match. And if you make all these little tiny processors that match this pattern and work all together on the same data, you can make a really fast system that compares this data. And, well, this is how the Force 10 P10 is really working. All tiny, tiny processors that compare a pattern on a small piece of the same data. And what this system really does is, on compile time, putting these rules in. And by that, sharing between different rules, different components, different resources in that FPGA. And this is how they can get so many rules into one FPGA. But for troubleshooting purposes, like we want to use it, that's not really a good approach, because troubleshooting is by definition dynamic. You want to have, you don't know what pattern you want to match against until you know what you want to do. With security, you have tons and tons of known attacks you want to match against, and you can compile that into an ideal set of ideal bit stream that you can put into your FPGA. So what I did is making these things dynamic. You can put patterns into these registers from the host PC to these tiny processors. Another thing was that these processors were really made for IDS purposes. They could not match on something that was not there. They can only match on something that's there. And it took me a while to figure out, hey, an IDS system is about matching patterns. It's not about not matching patterns. And remember this, not this source MAC address. For troubleshooting, you really want to match on something that is not there but should be there. So a not operator has to be built in. It's not really difficult, but it wasn't there. I didn't tell how this thing is working. So here in this register there's a pattern. Here, this is this 128-bit word that is being copied into this processor and it's being compared with each other. And if it fits, and it also fits the offset where it should be, then, well, this is being 1, and your whole rules together make that the frame is being copied to the PC or not being copied to the PC. I hope this is understandable. So, I explain it here a bit better. So we have this source MAC address, and on the first word we match in register X the pattern of that piece of the MAC address we want to match against. Then the second word comes in. For that we need 2 of these processors, if you will, to match it against. One processor matches 16 bits, and that together with the first matching makes that you can really look at filter traffic you are interested in that is coming by with 14.8 million frames per second. And to do that, Meta Networks made what they call an API. Basically, it's a description of the signals that are there in the FPGA and building blocks that they have, which they call the memory management. That is for the SRAM. The packet processor that's really making this, really processing this frame that's coming in and does some basic counting. And some signals from the front-end FPGA and some signals from the host. And a signal to capture the match memory and also a signal to block frames, if you will. And it's just a description, nothing else. You have to make your own functionality there in either Verilog or that other language. I forgot. So, working with this, I thought, hey, you can make a counter. Just count frames, because we can only capture 600,000 frames per second to the PC, and that's already a lot. But sometimes just counting an event just helps, and so we made a counter. And of course you can make multiple counters. So you can program different events that are going on. Another thing is that this counter is resettable, so it's, if you are really looking for a problem and you see this counter counting up to a zillion, you want to say, is it now over, and you don't know, so you can zero it and then see if it comes up again. That's a really handy feature. Sometimes you don't know what you are looking for. The traffic is way too high to capture, so it was also handy to make a sort of random sampler that is just taking frames out randomly out of the stream, copying it to the PC, reducing the data rate, a bit like SFlow is working as well. And that consisted just as a frame counter that controls a random number generator. Actually, the random number generator is constantly making numbers. And once the frame counter counted one up, it's copying that random number into this register, and it's just compared to that next frame counter, and that makes that there's a sample going out. I haven't really used this feature, but it might be handy in the future. It was easy to program. Another thing is, on troubleshooting, you also want to look at frame checksums, or not really frame checksums, but checksums in the IP header, or checksum, TCP checksum, or ICMP checksums, or UDP checksums, just to see if this tuple is being changed in Buddle somewhere. That makes that the frame checksum doesn't match. And this turned out to really, really hard one, because that force10 system is giving you frames in all kinds of words, and then suddenly you get a new frame. It doesn't tell you, hey, this is the end of the frame. And TCP and UDP checksums and ICMP checksums are really calculated over the entire packet. So your packet is there, you can calculate your checksum, and then you say, hey, this was the packet I'm interested in, but it's already gone. I didn't solve this solution yet, didn't solve this yet, but I have any idea on how to work on it. One thing could be using the length field. Yeah. But the length field, I think it's kind of dodgy solution, because you work with the data, you use the data that you want to work with. So the solution is probably in the front end FPGA, where you know where the end of the frame is. And then you also know that you might have a frame that's too long or a frame that's too short, and you can trigger on that as well. And this is actually where the project is right now. A future solution, future wish, is using this SRAM memory. Because remember this example 1, where we had one frame before that was actually causing the problem that you were looking at. So it might be handy to store the different frames coming by, and then have a trigger and have the frames before that, basically looking back in time. For that, this SRAM is a handy resource to have. But the problem is that the API from force10 really doesn't describe how this SRAM is working, and I have to reverse engineer that part, unfortunately. So this is where the project is now, and we still have 15 minutes left, so there's a lot of time for questions. A question there. Can you please wait for the microphone?
You said that the main processor contains these snort rules. I realize that you may not be using those at the moment. Is it just the rules, or is there any pre-processing done? Because I would think that would really interfere with your monitoring if the pre-processors were being used before you actually looked at the package.
Yes. The pre-processor is I didn't draw it. It's